And welcome to Chapter 9, which is gases. All right, so when we talk about our gases, right, the first thing that we need to understand is that gases are all about the different variables or the state variables that they're under. So gases are described by the volume that they take up, the amount of the gas, that's our number of moles of our gas, the temperature at which they're at, and the pressure. And so all of our problems, if we can get them in the right units, then we can plug them into our different calculations and solve for those. So let's see what we've got here. So volume, amount, and temperature, we're going to throw those all together, and then we're going to look at pressure kind of separate because pressure has a whole bunch of different units and everything like that that are associated with it. So all right. I'm going to remind ourselves here before I move on that our temperature is in the Kelvin scale, right? And so we take anything that's in Celsius and add 273.15 to that. And the amount of gas needs to be in our number of moles. Our volume, right, can be in liters, milliliters, or cubic centimeters. And when it comes to our problems, right, we really want to get things in liters. Right, so our gas is going to expand, and gases take up a lot of space, and that's why we usually will report our gases in liters. All right, pressure. Right, pressure is given as the force per unit area, and in the English system or in the United States, we might have heard of this as being in pounds per square inch. Right, you might see this on like a bike tire, right, or a basketball, right? If you're filling those, you might see that you want to put it into some PSIs there, right? But of course, we're the only country really that uses the English system, and everybody else out there uses other things. And so technically, right, the bar, which is BAR, is the SI unit for gases, right? But realistically, like we usually use atmospheres, all right, which are ATMs. And atmospheric pressure is about 14.7 psi at sea level. Another way of saying that is that one atmosphere is equal to 14.7 pounds per square inch. And if we are remembering, right, that means that we could use this as a conversion factor as one atmosphere per 14.7 psi or 14.7 psi per one atmosphere. Right. Another unit of pressure that we might see a lot of the time is in millimeters of mercury. That says mmHg out there. All right, and so one atmosphere is equal to 760 millimeters of mercury. So again, one atmosphere per 760 millimeters of mercury, or 760 millimeters of mercury per one atmosphere, depending on how we want to do a conversion. There's also something there, you might hear something called a torr. Okay, a torr is the exact same thing as a millimeter of mercury. It's just a different name for it. So if you see that, right, it's also the exact same conversion factors for it. So a lot of these things show up here on our other units of pressure slide. So we've gone through many of these, right? One atmosphere is 14.7 psi's. It is 760 millimeters of mercury in the US, right? Because we don't usually use millimeters. One atmosphere is 29.92 inches of mercury. This we might hear, right, when we talk about, right, barometric pressure. right? That is in like weather forecasts. Well, you did not spell that correctly whatsoever. All right, weather forecasts use like inches of mercury a lot of times in the United States. So if you might hear that, oh, the pressure outside is 30.02, right, inches of mercury, and it is rising or lowering. So they use kind of those units. Right, again, oh, sorry, the SI unit for this is the Pascal. I said it was the bar. I goofed on that, right? A bar is 1 times 10 to the 5th Pascal. So a bar is used a lot, but a bar is really, really tiny, and a Pascal is really, really big. Or sorry, a Pascal is really, really small, and a bar is big in comparison. Why did I goof on that? Anyway, we don't use the SI unit for it anyway. We use atmospheres whenever we're going to be dealing with our gases. All right, a Pascal is the pressure exerted by a 0.1 millimeter high film of water exerted on, like, say, the surface below it. And think about, like, 0.1 millimeters is really, really small. So if you have a 0.1 millimeter film of, like, water, how much pressure could that actually be exerting? It is a really, really small amount. And so even though the SI unit is a Pascal, we never really use a Pascal. Right, and realistically, right, we're going to be doing a lot of conversions, and we probably won't even use pascals anywhere to convert from one thing to another, because it is such kind of like a useless, thing when it comes to the pressure of gases. So we're not going to really stumble across that very much. Okay, gas laws though are all about doing a bunch of different conversions. Okay, so gas laws are about getting the right units for our volume, our pressure, our temperature, and our amount. You got to get everything in the right units. And gas law problems are notorious for giving the wrong units for things. Because once you have everything in the right units, it's pretty simple to plug them into the gas law equations and solve for what we're looking for. So every time you have a gas law problem, really look at yourself and be like, do I have the correct units before moving on? All right, so get used to doing all of these conversions because you're going to do them a bunch of times, and then they should be like second hat to you pretty darn soon. All right, so let's look at then the ideal gas law, which is once we get everything in the right units, we are going to plug things into the ideal gas law. So the ideal gas law is if we were to take a hypothetical ideal gas, which means that gases are behaving in ideal behavioral spaces. And not all gases are going to be ideal, but for our purposes, we're going to assume that all of our gases are ideal gases. Okay. So we've got some statements here that volume is directly proportional to the amount. All right, so think about this. If you have a balloon, right, and you blow a balloon up, right, the balloon gets bigger as you blow more gas molecules into it, right? So the volume gets bigger as you increase the amount. They are directly proportional to each other. Volume is directly proportional to absolute temperature. So an absolute temperature just means that we're dealing with the temperature on the Kelvin scale. So think about taking a balloon, right? And I promise if you haven't done this, if you do it, like take a balloon, blow it up, and then put it in a freezer and come back and look at it, and the balloon will have shrank, all right? Because as the temperature goes down, the volume of the gas goes down as well. So as one goes one direction, the other goes the same direction. So they are proportional, directly proportional to each other. Their volume is inversely proportional to pressure. So again, if you took a balloon, it's hard to do with a balloon because balloons are kind of pliable and stuff. But if you were to squeeze in the gases, right, as you put more and more pressure on something, you can tighten up those gas molecules and the volume goes down. So as the pressure goes up, the volume is going to go down. They are inversely proportional to each other. Right, and that is related to our ideal gas law equation then. All right, and so if we do our ideal gas law equation, right, pressure and volume are on the same side of our equal sign there. And when two things are on the same side of an equal sign like that, that means that they are inversely related to each other. All right, and then notice though that on the other side of the equation is N, the amount, and T, which is our temperature. All right, and we just said that volume is directly proportional. Things on opposite sides of an equal sign like that are directly proportional to each other. So our equation is PV equals nRT, where R is a gas constant. All right, and R was experimentally determined, and it happens to be 0.0821 liter atmospheres per mole Kelvin when we are using this equation. Now we'll come across and we'll see that there are other R's, there are other R gas constants out there, but for any time we use the ideal gas law, we're going to use this as our equation. All right, so there are three types of problems where we can use the ideal gas law. All right, so number one is we can solve what we call the final state of a gas, knowing its initial state and how it changes over time. All right, we're going to do a sample problem of each one of these three, don't worry. So I'm going to kind of breeze over it here, and then we're going to see that. Okay, and when we've got a final state of a gas knowing its initial state, we're going to write the ideal gas law twice. Okay, and so it's going to be like P1 V1 is equal to N1 R T1. And we're going to set that whole thing equal to P2 V2 is equal to N2 R T2. So anytime we have an initial and final state problem, that's how we're going to solve that. We'll see that in just another slide from here. We have single state problems where if we don't know one of the four variables, we can solve for it. Okay, so in that case, I'll write that up here. We have PV equals nRT. So if you are solving for pressure, it's nRT over V. If you were solving for volume, it is nRT over pressure. If you're solving for amount, it's PV over RT. And if you were solving for temperature, it is PV over RN, right, or NR. Right? And so all we're doing there is like we know the other three, and we don't happen to know the final one. And then lastly, we can also solve for the density, right, by determining the molar mass of our gas. And I'm not going to write the equation for that because I want to show it whenever we get to that one. But in that case, we can also use our ideal gas law to solve for densities. Okay, so let's then solve for a final and initial state problem. Okay, so again, this is where our gas is going to undergo some sort of a change over time. All right, and like I said, we're going to take our ideal gas law, we're going to write it twice and set them equal to each other. And then we're going to get rid of anything that remains constant over time. So I have a 2.5 liter volume of hydrogen is measured at a negative 196 degrees Celsius, and it is warmed up to 100 degrees Celsius. Calculate the volume of the gas at the higher temperature, assuming that we have no change in pressure, and obviously then we didn't change the number of moles of our gas, right? It's not like we added any moles of gas. It doesn't say anything about that in here. Okay, so what I'm going to do is I'm going to start by writing the ideal gas law twice. P1V1 is equal to N1 RT1, and I'm going to set that whole thing equal to P2V2 is equal to N2 RT2. Okay, I'm going to get rid of anything that was a constant in this problem here. Okay, so, right, the amount remained constant, right, because we didn't change the amount of gas in there. It says that there was no change in pressure, so we're going to cancel out our pressures. And R, by definition, is a constant. So let's get rid of our r's as well. So this then simplifies to V1 is equal to T1, and that whole thing is equal to V2 is equal to T2. Now, when you have things that are equal to each other, you can write them as ratios. And so another way of writing this is V1 over T1 is equal to V2 over T2. All right. Now, the next thing I'm going to do before we get too far along is I'm going to say, okay, I'm going to call volume 1 2.5 liters. And I'm going to call temperature 1 negative 196, but we need Kelvin. So let's add 273 to that. Could add 273.15, but come on, we're not going to do that. So this is going to be 77 Kelvin. V2 is what we're looking for, and T2 is 100 plus 273, 373 Kelvin. All right, so let's plug in now. I have 2.5 divided by 77, I'm running out of space down there, is equal to, all right, V2 over 373. All right, or 2.5 liters times 373 Kelvin over 77 Kelvin is equal to V2. And so our new volume then is going to be 12.1 liters. And I can ask myself, does that make sense? The volume got bigger. Well, remember, temperature and volume are directly proportional. So as the temperature went up, the volume of the gas went up. Yes, it did. All right, that makes some sense. All right, that's how you're going to do any initial and final state problems. All right, next off, easiest ones are probably our single state problems, right? And again, this one says that if you've got a single state problem, we just have one of the variables that we don't know. So in this case here, right, it asks how many grams of gas are present in the following case. I have 1 liter of carbon dioxide at 307 torr and 26 degrees Celsius. Okay, so in this case, we have PV equals nRT, or, right, we want amount. Now it says that we're going to do grams, but I can't do that here, but we can get to grams. So that's fine for the amount, because we don't know that, is equal to PV over RT. All right, well, we got some issues, though, right, because the volume is 0.1 liters, that's good, but our pressure is 307 torr. Okay, but we need that to be in atmospheres, right? I told you they're notorious about giving us the wrong units. Okay, so what we're going to do then is we're going to solve for that. And so 1 atmosphere per 760 torr is equal to 0.404 atmospheres. And then I've got my temperature as 26 degrees Celsius, but we got to add 273 to that. That is 299 Kelvin. Now we can plug in. So we have N is equal to, all right, 0.404 atmospheres. So pressure times our volume of 0.1 liters divided by our R. Our R is 0.0821 liters times atmospheres per moles times kelvins. All right, times our temperature, 299 Kelvin. All right, so look at all these units go away. Atmospheres cancels with atmospheres in our gas constant. Liters cancels with liters in our gas constant. And kelvins cancel with kelvins in our gas constant. And now I've got those moles, and they're in the denominator of the denominator, so they're actually on top. So when I solve for this, I get 1.65 times 10 to the minus third moles of CO2. All right, but it asks us, we've done most of the work here, but it asks us for the grams. So now what we're going to do is we're going to do some stuff that we did earlier in the chapter where we're going to convert this into grams by using the molar mass. Right, and CO2 happens to weigh 44.01 grams per mole. All right, so this ends up being 0.0724 grams of carbon dioxide. Okay, that's what we do for our single state problems, right? Whichever one we're missing, we solve for it. All right, next up, let's do molar mass and density problem. Okay, so let's recall from earlier that density is mass over volume. All right, and if we think back to the fact that molar mass has units of grams, which is mass, per mole. Okay, now let's look at our ideal gas law and think about it, right? The number of moles is in the ideal gas law, right? And the number of moles could be grams per molar mass. Right, as gram mass divided by molar mass is moles, right, by looking at those units there. And there's also a volume in our ideal gas law, if we notice that. Okay, so what we can do then is we can rearrange some things there, and we can take PV equals nRT, and what I've done is I've taken my N and I've turned it into mass divided by the molar mass. And then if I rearrange it a little bit more, and I do mass divided by volume, that's density, then our density is equal to pressure times the molar mass of our gas divided by our gas constant times the temperature in there. Right, so this is something called like deriving equations, which I'm usually not really big on having you guys derive equations, but I wanted to show you that, you know, we could get there from looking at all the units and playing around with things there. All right, so let's calculate a problem of the density. Calculate the density of Freon at 30 degrees Celsius and 0.954 atmospheres. So, right, density is pressure times molar mass over R times T. So, our pressure is 0.954 atmospheres. The molar mass, okay, so the molar mass of Freon happens to be 120.92 grams per mole. Okay, and we're going to divide that by our R, 0.0821 liter atmospheres per mole Kelvin, times our temperature, 30 degrees Celsius, but we want kelvins, right? So 30 plus 273, 303 Kelvin. All right, now we're going to check and we're going to say, okay, I got moles on the bottom up here and moles on the bottom down here. Those cancel. I have atmospheres on top, atmospheres on the bottom. Those cancel. These kelvins cancel each other. All right, I'm going to end up with units of grams per liter. That's the units of density. Hey, perfect. So then our density for this is going to equal 4.64 grams per liter. All right, it works. So those are the three different types of ideal gas law problems that we might run across. Okay, now the other thing that we can do with our gas law problems is we might run into the stoichiometry of gas laws, all right? Because, right, we can really do stoichiometry like we've done before, but we're just going to take it one step further. So if you could do stoichiometry of other things, then we're really not going to be doing anything that's that much different here. Okay, now remember that gases can be reactants and products depending on, how they're reacting together. And just like, liquids and solids are aqueous things, they're in a balanced chemical equation. They've got coefficients out in front that we can look at. And so when we've got that, we can relate the number of moles of one species to another. And if you remember earlier, right, we could go from grams of something to grams of something else. Oops, I'm going to do this by saying that we could go to moles of that something to moles of something else. And then we could finally end up with that grams of that other thing. Okay, well, now that we've got our ideal gas law, and we have PV equals nRT, right, and N, right, we could, is the number of moles of something. What I really could do is I could go from the grams of something to the moles of that something to the moles of something else, and then using PV equals nRT, I could find the volume of that gas. Right, so instead of going to grams, we're just going to be able to go from volume by using our ideal gas law there. All right, so let's look at a sample problem of this, right? I've got the reaction occurred at 427 Kelvin with 37 grams of CH4CH4 and an excess of oxygen. It says that the carbon dioxide that was produced, right, is in a 30-liter container. What is the pressure within this container? Okay, so, right, we want to find the number of moles of what we are interested in then use stoichiometry. Okay, so, right, I have 37 grams of CH4, CH4, all right, and this is just one CH4. I don't know what happened there. Okay, it was like something's off with that. It didn't make any sense because that is not a compound. Okay, I got it eventually. So there is 1 mole, right, per, okay, what does CH4 weigh? Well, 12 plus our 4s, and so we get 16.05 grams per mole on that. Okay, and so that would give us our moles of our methane. Okay, but we want the pressure of the carbon dioxide. So why don't we find then, we're looking for the number of moles of what we're interested in, which is the carbon dioxide. So I can use our stoichiometry here, and I can say, okay, I have 1 mole of carbon dioxide, right? That's from our balanced equation there. There's 1 as a coefficient out in front. For every 1 mole of CH4. All right, so this gives me the moles of our carbon dioxide, right? And that is going to be 2.3 moles of CO2. All right, now we can use the ideal gas law. So we're looking for pressure, right? And once we get to this point, it's just a single state problem all the time. So pressure is equal to nRT over V. So we just found the number of moles, 2.3 moles, or R, 0.0821 liter atmospheres per mole Kelvin, right? So notice that the gas constant has all of the right units. So if you are working through a problem and you forget what units that you need things to be in, it's right there in the ideal gas law constant. Our temperature is in Kelvin, 427 Kelvin. We're going to divide that by our volume, 30 liters. Great. Let's double check all of our units. Our liters cancel with liters, our moles cancel with moles, and our kelvins and kelvins cancel, and we have atmospheres. Perfect. So our pressure in this case is 2.7 atmospheres. We got it. All right. Next stop is partial pressures and mole fractions. Okay, the good news is that the ideal gas law works for every single gas that's out there. It does not matter if it's hydrogen, carbon dioxide, oxygen, whatever the gas is, however big or small, the ideal gas law works perfectly. And this, it works for mixtures of gases as well. Right, when we have mixtures of gases, then we're going to come up with a new term that we call things, and that is the partial pressure of a gas. Okay, so if you have a mixture of gases, right, the total pressure is the sum of the partial pressures of all the individual gases. All right, so that's like gas number 1, gas 2, gas 3, so that could be, you know, the partial pressure of water vapor plus the partial pressure of carbon dioxide, whatever all the gases are that are present in there. Okay, now, when we've got this, we can also use the partial pressure of these gases to find something that we're going to call the mole fraction. All right, so to find the mole fraction, all right, the mole fraction is given by the symbol of chi, right? That's an x as far as we're concerned, right? So the mole fraction of some gas A, actually the mole fraction for anything, but we're talking about gases here. So the mole fraction for something A is the number of moles of whatever we're talking about divided by the total number of moles. Right, now, if this was a percent, we would multiply by 100. But it's not a percent, it's a fraction. So it's the same sort of a setup, but we're not getting a percent, so we're not multiplying by 100 there at the end. Okay, so the mole fraction is that. All right, but because of our ideal gas law, PV equals nRT, and that pressure and N are directly related, right? As pressure goes up, the number of moles goes up, then it's also that the mole fraction of A can also be written as the partial pressure of A divided by the total pressure of all the gases. Okay, so that is all of those things there. And if we rearrange something there, we can find the partial pressure of gas A, right, is equal to the mole fraction times the total pressure. All right, so let's do a sample problem of that here. Okay, when 1 mole of methane is heated with 4 moles of oxygen, we get this following reaction of methane plus 2 oxygens producing carbon dioxide and some waters. If all the methane is used up, right, what are the mole fractions of oxygen, carbon dioxide, and water in the resulting mixture? Okay, so when we get here, I'm going to write what we call an ICE table. All right, might be the first time we've seen an ice table, and it won't be the last if you're going on to our Chem 2. All right, but here I've got my CH4. I've got 2 oxygens. They're producing our carbon dioxide and my 2 waters. Okay, so initially, right, that's the I in my ice table. Initially, right, what did it tell me that I had? I had 1 mole of methane and 4 moles of oxygen. All right, and thus we had none of those other things quite yet. All right, and now we've got a change. That is the C in our ice table. That's our change. Okay, it says all of the methane is used up. So that goes down by 1 mole. All right, and if we look at the coefficients out in front, if that goes down by 1 mole, then the oxygen is going to go down by twice as much. Right, that's where I'm getting that 2 from there. And then on the other side of the arrow, since those are going down, the other side, they're going to be going up. And so if the methane goes down by 1, and the carbon dioxide then has to go up by 1, because they're 1 to 1. And if the methane goes down by 1, then the water is going to go up by 1. Okay, so at the end of this reaction, right, ice. It's an ice table. At the end of this reaction, I have 0 of my ammonia, of methane, sorry. I have 2 moles of oxygen, 1 mole of carbon dioxide, and 2 moles of water. Okay, so that's shown down here, right? So that's how I got all of these values by setting up that ice table to see how things reacted together there. Okay, now, right, if the total mixture has a pressure of 1.26 atmospheres, what are each one of the partial pressures going to be? Okay, so let's see. Total moles of the gas is 1 plus 2 plus 2, right? There was 1 mole of our carbon dioxide, 2 moles of water, and 2 moles of oxygen. And there was none of our methane. So that is 5 moles total. All right, so then the mole fraction of the carbon dioxide is, well, there was 1 mole of CO2 divided by 5 moles total, and so the mole fraction of this is 0.2. The mole fraction of water is going to be the same as the mole fraction of oxygen, by the way, so I'm going to write them together here. I'm going to say that those are 2 moles of them divided by 5 moles total, which is 0.4. All right, I want to point out that the sum or the total, the sum of the mole fractions should equal 1. 0.2 plus 0.4 plus 0.4 is 1. They add up to being 1. It's kind of like the sum of percentages should equal 100%. Same idea here. They have to equal 1. Okay, so now we've got the total pressure and we have the mole fractions of each one of these. Okay, so the partial pressure for CO2 is the mole fraction of the CO2, which is 0.2, times the total pressure, 1.26 atmospheres, which is 0.252 atmospheres. All right, I'm going to do this for water and oxygen as well. Both of them have mole fractions of 0.4. The total pressure is still 1.26. All right, and so those are each 0.504 atmospheres. Okay, now, right, we can check this because remember, the total pressure should be the sum of all the partial pressures. So if I add all of these together, they add up to be 1.26 atmospheres. That works. Okay, lastly, we're going to do a little bit on the kinetic theory of gases. We're not going to go super in depth on the kinetic theory of gases, but I want to bring up like something just so we understand how freaking fast gases are moving around us at all times. Okay, so gases are mostly empty space, all right? Liquids are stuck together. The atoms are stuck together. Solids, they're tightly packed. Gases are moving around, they're free to move around, and there's a bunch of empty space in between each gas molecule. All right, and so even though the volume of the gas might be relatively big, right, if you were to condense the volume of all the molecules, they would be really small because there's so much empty space in there. All right, gas molecules are in constant random motion, and when they collide with each other, they are elastic collisions, meaning that they don't slow down. So when they bounce off of each other, they're going to bounce off of each other, and they're going to have the exact same speed as they did when they did. So they're not slowing down over time because of that. Right, and then the pressure on something is because the gas particles are bouncing into the sides of a container. So the harder they're bouncing into the sides of a container, the higher the pressure is going to be. Okay, so, that is translational motion. Translational motion is the motion in a straight line of something. Right, at a given temperature, all the molecules of a gas have the same average kinetic energy. Okay, now that doesn't mean each one of them has the exact same kinetic energy. It's just like averaged over them all. Right, they're going to average out to have the exact same average kinetic energy. And we can calculate that. And it is directly proportional to the temperature and inversely proportional to the molar mass. Right, because molar mass is on the bottom of this here, It's in the denominator. Okay, the equation here is that the average kinetic energy, the speed here, actually, the speed in this case is equal to 3 RT over molar mass to the 1/2 power. All right, and so R in this case is a different R. Okay, so we've got 3 different R's. This one is the second one that we've come across. It's the third one that would come up in Chem 2. And this one is 8.31 times 10 to the third, all right? And it has units of grams times meters squared over seconds squared times moles times Kelvin. It has these crazy units in there. All right, we're going to do one average speed of something as an example just to kind of see this played out. It says calculate the average speed of carbon dioxide at 20 degrees Celsius in meters per second, which is the easy thing, and then we're going to convert it to miles per hour just so you understand how fast, because meters per second probably doesn't mean a lot to us, that are native people here in the United States. All right, so, in order to calculate this, our U is equal to 3 times our R, 8.31 times 10 to the third grams times meters squared over seconds squared times moles times Kelvin. Oh boy, that's a lot. And then, we are going to take that times our temperature in Kelvin, So 20 degrees Celsius is 293 Kelvin. We're going to divide this by the molar mass, and this is carbon dioxide. So the molar mass of that is 44.01 grams per mole. Okay, and we're going to take this and raise it to the 1/2 power. So we get this. I'm going to have my grams are going to go away, my moles are going to go away, my kelvins are going to go away, and I have meters squared over seconds squared, but we're going to raise it to the 1/2 power, so really it's going to end up with meters per second. That's a speed of something. So, right, remember to take the square root of this at the end, right? It's really easy to forget that. So anyway, we get this to be 407 meters per second. Right? Gases are whipping around. Now let's see what that is in miles per hour so we can see that. So this is just a simple conversion of doing unit conversions that we started learning way back in chapter 2. Actually, probably chapter 1. Right? We have 1 mile per 1,609 meters. All right, so this would be miles per second. And there are 3,600 seconds per hour. All right, so seconds go away. I have miles per hour here. Okay, this is then, all right, carbon dioxide at 20 degrees Celsius, a little below room temperature, but not by much, is moving around at 912 miles an hour. Other gases like oxygen and nitrogen that we're breathing in are also moving at kind of pretty close to those speeds, not exactly because their molar masses are a little bit different. But they are whipping around, right? And so remember, temperature is actually a measurement of how fast something is moving. So they're colliding with that thermometer and they're transferring energy into it. The faster the molecules move, the higher the temperature, right? So remember, at a higher temperature, right? Right? This would be bigger as well. All right, that ends chapter 9, gases. Our next chapter is all about liquids and solids, and I'll see you guys then.